Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 21. So, till last class what we are discussing is the time correlated single photon counting setup, and I already mentioned you that we will going to discuss two types of method for the lifetime measurement. So, the first one which I have already discussed is this time correlated single photon counting, and probably by now you have fair idea about the principle of this system and how does it work. So, now we will going to discuss the fluorescence up conversion. Let me tell you that each of these method has its own advantage as well as disadvantage. Let me talk about the disadvantage. For this time correlated single photon counting, for this TCSPC, the disadvantage is the IRF. Even for the very modern setup, the IRF is just about 25 picosecond. It means that if you want to measure the dynamics of any such kind of process involving the fluorescence, the dynamics, you cannot measure a dynamics which is less than the 25 picosecond. But actually because of this iterative reconvolution technique, one can report a time constant of 1/10, theoretically 1/10 of this IRF. So, even that it could be only 2.5 picosecond or 3 picosecond. So, if something is happening less than that time scale, you will not going to have any clue about the time scale of that process. So, you need a better time resolution setup, that means the IRF must be in that time resolution, that means about 0.1 or 0.2 picosecond, then you will be able to find out those type of dynamics. So, for that this fluorescence upconversion is the technique where the time resolution is about 0.2 to 0.4 picosecond as is written over here. The disadvantage here, the time window is small, it could be 1 to 2 nanosecond, but here the time window is really large, it can go to the microsecond or millisecond time region. Okay. As I already have discussed, why this IRF is limited to 25 picosecond? The reason behind it is the transit time spread of the detector. The another reason is that inherent that CFD, what is that form of the CFD, and the third one is the laser pulse width. Even I change this laser pulse width from 20 picosecond to 20 femtosecond, I have already showed you that there will be no change in the IRF, because this IRF is mostly guided by these two. And you cannot buy a better detector than this what detector has been used to get this 25 picosecond IRF. You cannot buy that better detector than this. It means that if I follow the working principle of this TCSPC system, I will never be able to achieve a time resolution or IRF less than 25 picosecond. But if you are interested in measuring the dynamics which is much faster than this, then what you have to do? You have to go for a different type of arrangement by which you will be able to get a much shorter IRF. So, that technique is the fluorescence upconversion technique, and to discuss this technique I need to discuss a few things, just a few things, otherwise I will not be able to discuss this technique. So, that thing is the polarization. Usually denoted as P, right. What is polarization? So, when a substance or material is placed under the electric field, then there is a induced dipole moment because of the oscillation of this electric field, right, inside this material. So, induced dipole moment per unit volume is known as the polarization. So, this polarization is a function of electric field that I know, and for some molecule it is easy to polarize it, and for some molecule it is not easy to polarize the same. That means, for some molecule the creation of induced dipole moment is more, and for some substance the creation of induced dipole moment is less. So, this is a molecular property. So, that is also proportional to molecular property chi 1. So, I can simply write this P is equal to chi 1 E, right. So, that we have, you have probably seen this type of equation, this is a polarization, right. So, if I increase the strength of this electric field, that means intensity is E square, right. So, now if I increase the intensity of the light, then the induced polarization will increase because E is increased, that so the induced dipole moment will increase, that means polarization will increase of the system. If I now plot this P versus E, then I will get a straight line, right, because this P is some constant into E. But if you extend it, what people have seen that this line deviates from the linearity, this line deviates from the linearity, and some non-linear effect comes into the picture. In this case this is linear, over here it is non-linear. So, this non-linearity of the polarization was explained by this equation, P is equal to chi 1 E plus chi 2 E square plus chi 3 E cube, so on, right. So, let me take a functional form of this electric field, right, the cos omega t, I can think of it, right. So, with a amplitude E 0. So, let us say the E in this case. So, this is the first order, this is the first order, this is the second order, this is the third order, and so on and so forth. Okay. So, now if I think that E is equal to E 0 cos omega t, so this is the frequency, then if only first order term is available, right. So, if I approximate that this equation is only till over here, then what I will do, I will simply write P is equal to chi 1 E 0 cosine omega t. So, you see that polarization, that means induced dipole moment, this polarization is also oscillate with this same frequency, right. That means, the color of light which will come out of from here will be the same color of this, because it is the same frequency. So, color is the same. Now, if I take that P equal to chi 1 E plus chi 2 E square, both the term, if you want you can take the third one or fourth one and so on, but please remember that this chi 3 is much smaller than chi 2 and which is much smaller than chi 1. It means that when the value of E is small, as this is much smaller than this and this is much smaller than this, then the contribution will only come from the chi 1 E. The contribution from the second term, third term, fourth term will be negligible. The contribution from the second term will be there measurable only when the E is very high, right. Then E square will be very high, and then the although this chi 2 is much smaller than chi 1, probably we will be able to see some contribution. And this kind of effect is only visible when the power of the light is very high, which is the case for the laser. Otherwise, for normal light, such kind of nonlinear effect is not visible. But with the laser, as I mentioned briefly, the one of the property of the laser is that the laser has a very high power, then only we will be able to see this nonlinear effect. Okay. Now, let us take the same functional form as that what I have wrote over here in this case. So, I will just simply write here chi 1 E 0 cosine omega t plus chi 2, here it will be E 0 square, right, and this is cosine omega t and again cosine omega t 2 times. So, this is like a cos A cos B type of formula. So, this part will going to give you cosine twice omega t term. So, what you see, you have this omega term as well as this 2 omega term, both the term is present for this polarization. That means, the light which will come out of this system will have both the frequency that is actually hitting the substance and just the double of that frequency, which is 2 omega. Please note here. So, you have this omega here and you have this 2 omega here. That means, the color of light will change, the frequency will become double. Okay. Now, consider that you are using two different lights of frequency omega 1 and omega 2. In this case, that second order polarization will be equal to chi 2 E 0 1, that is that one kind of light, the cosine omega 1 t and E 0 2 cosine omega 2 t. These are two different color of this light, right, two different lights. That means, this is chi 2 E 0 1 E 0 2, and then what I will going to have, all those things will be there, like let me take it outside. So, basically what I will going to have is cosine omega 1 plus omega 2 t, and I will also get another term plus cosine omega 1 minus omega 2 t, right. I will get these two terms. So, you note here that this term is the summation of these two frequency, and this is called the sum frequency generation, and in this case it is just a difference. So, this is known as difference frequency generation. Okay. What we have seen is that this is the sum frequency generation, and this case is a special case of this sum frequency generation when both the color omega 1 and omega 2 they are same and equal to omega. So, here is this is a special case, and this special case is known as second harmonic generation. That is it. with this background, let me continue. Okay, let me also tell you that what is the implication of this. This means that if you have a light of 800 nanometer coming and hitting a substance which is called the nonlinear active material, right. In that case, the value of chi 2 is high compared to the other substance, and it has a special characteristics that it is a non-centrosymmetric. I am not going to discuss all the details because obviously the nature of this course. So, this has to be non-centrosymmetric in nature. Non-centrosymmetric in nature. Then it can, that same 800 nanometer light will come through, 800 nanometer light will come through, but along with that another light, that is, this is, if this is my omega, then 2 omega light will also come. So, for this 2 omega it will be obviously will going to have a different color. So, from here the 2 omega light will also come, which is nothing but the 400 nanometer, right. Simply if you take not 800, if you take some other light, let us say 1100 nanometer, then your output will be 1100 nanometer as well as 550 nanometer. Okay. Now, if I do something else, if I take the light, one light along this direction and another light along this direction, and the color of these two lights are not same. Let us say one light is 800 nanometer and another light is 600 nanometer, right. Then this 600 nanometer light, after passing through this NLO material, right, will produce 600 as well as 300 nanometer, and this 800 nanometer light will produce 400 as well as 800 nanometer light. But these two light will also mix together in NLO crystal, and that will going to produce another kind of light which will come along this direction, and that light will be the some frequency generation light. Here is my omega 1 plus omega 2. So, in this case this value will be 342 nanometer. So, this is property. So, I am not going to describe exact all the mathematics behind it, but take it granted that this light will be along this path, and here this is simple, right. This is 1 over 800 plus 1 over 600 inverse is going to give you this value, that is for sure, that is no problem. So, this is just omega 1 plus omega 2, because this is 1 over, I have just used this as a wavelength. So, I have changed it to the wave number and then again inverse it. So, that is it. Okay. Now, remember that such process will take place only when both the lights are present inside the NLO crystal. If only one light is present, that means if only the 800 nanometer light will present, then the output will be 800 and 400. If only 600 is present, then the output will be 600 and 300. But if both 800 and 600 will present, then only that some frequency will takes place and you will get a output along this direction with a wavelength of 342 nanometer. Okay. So, this is clear. Now, another important information I want to give you, then that will help me to tell you what is the fluorescence upconversion method. That information is what is speed of light. So, we all know the speed of light, it is 3 into 10 to the power 8 meter per second. It means light travels a distance of 0.3 micron in 1 femtosecond. So, 0.3 micrometer in 1 femtosecond. So, this distance travelled by this light. So, here you see this is my distance and here is my time. That means, these two are correlated with each other. So, if I measure the distance, I can estimate the time and vice versa. If you know the time, then you can measure the distance. In this particular case, in this particular fluorescence upconversion setup, I will going to show you that in this case distance is my time. Okay. Now, let us proceed. Now, let me draw a setup here. This is my laser, which is which can generate very short light pulse, because now my aim is to have the instrument response function of in the order of 100 or 200 or 300 femtosecond. So, obviously, if you use a light pulse of 200 picosecond, then instrument response function cannot be like a 100 or 200 femtosecond. So, you have to use, at least you have to use the light source as a 100 femtosecond light source. So, let me take this as 100 femtosecond pulse it can generate. So, now this light, what I will do, I will put some lens and this NLO crystal and another lens, and then I will put a beam splitter over here. So, this is my NLO. Now, let me take this red color, because let us consider that the wavelength of this emitted light from this laser, wavelength of this laser light is 800 nanometer. Let us consider, that means the color is reddish. So, it is giving me 800 nanometer light, but this light is not CW light, not continuous wave, this is the pulse light. So, light is present for some time and then rest of the time light is not present. Again probably at this position light is present, right. So, the difference between these two light is guided by the repetition rate of the laser, and it has some width which is already I have said is 100 femtosecond. Clear. So, for this is the laser light. So, the intensity is high, electric field strength is high, that means it will undergo NLO, because I said when the light intensity is high, then only it will undergo the NLO effect, otherwise not, right. So, in this case, when this red light will pass through this NLO, that 400 nanometer light will also produce, because it is 800 nanometer. So, 400 nanometer light will also produce. So, let me mark it like this blue. So, both the lights are coming from this NLO, and this beam splitter is a device where one color of, or this is not a beam splitter, sorry, this is a dichroic mirror. So, this is a dichroic mirror, this is a device where this one color of light will pass and another color will reflect. So, for example, in this case the blue light is getting reflected and this red light is transmitted through this dichroic mirror. So, I will get this red light at this side and the blue light at this side. Then we will do couple of things over here, which will put a device, right, which will I will going to discuss later. This device is the same device which I have skipped during the discussion of the TCSPC system. I said the polarizer, again here is similar kind of thing which I will going to discuss later. What is the necessity of this, I will going to discuss later. Then this light will be used, like just you can put another mirror over here, and then this light can be used to through some lens to excite your sample. here you have lens, and here you have your sample. So, you can excite the sample with this blue light, and then sample will generate the fluorescence, right. Fluorescence is typically, the color of fluorescence is different. Let us say I choose this green light as a fluorescence. So, fluorescence will come out in all the directions. So, this is my fluorescence light is coming out in all the direction, and you put something over here, some mirror or something, or a big lens to collect whatever the amount of fluorescence you can collect. Then this fluorescence will be collected at in this position, right. So, as much as you can, you collect the fluorescence, and this fluorescence will be guided along this pathway. Okay, what you do with this red light? You take this red light and make it come back from here to here to here, and put a mirror later and here, and you make it come over here. But in this case, what you will do, you use a mirror system which is movable, right. I will just show you here. You use a mirror system which is movable. This is a mirror system. That means, when the light will fall here, it will be reflected from this to this, and then it will go. But this whole system, right, is mounted on a stage which you can either push in this side, or you can take it in the front direction. Okay. And then you have a mirror here, you have another mirror here, and you put a big lens over here, so that this light will get focused in this pathway, and your fluorescence will also be focused along this pathway. And at this junction, right, where both this red and the fluorescence actually overlapping, what you do? You put one NLO crystal over here. That is it. This is my diagram. Here what I am trying to do? Now, this fluorescence will have its decay. It has a decay, it is a time dependent fluorescence, right. But this pulse is remain as this 100 femtosecond pulse, because some of the pulse is converted, only the intensity will go little down, but eventually this pulse will be still here, over here. So, this pulse will come over here, right. When this pulse will come over here, that you can guide by pushing this delay stage either in this direction or in this direction, that when you want that pulse to come here. Okay. Now, let me draw this fluorescence intensity decay of the sample and this pulse in this diagram below. Suppose this is your fluorescence intensity decay. Okay. And this is the position. Now, this fluorescence intensity decay will be there, it will be there for a given excitation pulse. The fluorescence will come at initially the intensity is maximum, then as time goes the intensity will become smaller and smaller, and at a very long time this will going to be 0. Now, when this femtosecond pulse 800 nanometer femtosecond pulse will come, that you can guide by moving this mirror system. So, you can choose that 800 nanometer pulse will come at this point of time, then the total intensity will be proportional to the intensity of this 800 nanometer light and the fluorescence intensity over here. So, this is movable. You can actually put wherever you want this 800 nanometer, that red one. Let me draw it in red color. then it will be easy for you to understand. So, this one you can actually move relativistically, right. So, if this is coming later, this is coming later at this position, that means it will coincide over here. So, at your desire it can be here, it can be over here, it can be over here, it can be over here. So, depending on the position of this two mirror system, right. Now, consider the case when this position of this femtosecond pulse, that 800 nanometer pulse is at this position where there is no fluorescence intensity. What will happen in this case? In this case, this fluorescence intensity as 0, that means one of the component is 0. You remember that omega 1 and omega 2, omega 1 plus omega 2, but it has its E 0 1 and E 0 2 for these two components. If one of them is 0, that product will be 0 automatically. So, I will not going to get any signal in this direction. I will not get any signal in this direction, right. But when the system is at this position, is just matching around this position. So, the intensity will increase a little bit, but when this system will be at this position, then there is a lot of intensity of the fluorescence, and this remain fixed, no? This 800 nanometer light, the red one, remain fixed. So, the intensity will increase, and as you move it from here to here, the intensity will again decrease, and if you move it from here to here, the intensity will be much smaller. That means, by scanning the position of this 800 nanometer pulse throughout this fluorescence decay, what I can do? I can measure this omega 1 plus omega 2 light intensity when omega 1 plus omega 2 intensity is high. I can simply say the fluorescence intensity is high, provided that 800 nanometer laser light intensity remains same. There is no fluctuation on that. Okay. So, I can plot the intensity of omega 1 plus omega 2 light, intensity of omega 1 plus omega 2 light as a function of the displacement here, and you remember I said that light travels 0.3 micron in 1 femtosecond. So, if I plot displacement, you can readily convert that displacement with time. So, displacement is time for me in this case. So, I can plot the time. What will happen when this light for 800 nanometer light is at this position, then I will get a 0 intensity over here. When it is over here, the intensity will increase little bit. When it is over here, then intensity will increase maximum, then the intensity will decay like that. The intensity profile of this omega 1 plus omega 2 as a function of t, this is my delay time, right, will be exactly same as the original fluorescence decay, provided the 800 nanometer light intensity remains same during your experiment. That is it. So, in this case, what you will going to see is that the time measurement is being done by the distance. There is no electronics is involved for the time measurements. For the time measurement in TCSPC, the electronics part, the detector was itself was involved for the time measurement. The CFD was used to reduce that time jitter induced by the amplitude jitter of the PMT. So, those electronics parts and the tag was there, that was working as a stopwatch, but here the time measurement is being done by these delay stage. and you go to any mechanical engineer or any shop that can create a mechanical device with a micrometer screw by which you can translate this 2 meter system with the precision of a micron, right. If you can move this as a precision of a micron, then right you are done. You can measure the time in that 1 femtosecond time region. So, if you can measure the time in 1 femtosecond time region, you should be able to get very high time resolution, that means very short IRF, and in this case the IRF only depends on the pulse width of the laser, right. There are some other factor like group velocity dispersion, these are, but I have decided not to discuss all those things. So, if you start with 100 femtosecond light pulse laser light, then your IRF could be 150 femtosecond. Those small changes because of mainly because of the GVD and other thing which I am not going to discuss. So, in this case what you can see is that as this setup is only optical and the time measurement is being done by the delay stage, right, just by the changing the distance, that is the measurement of the time. So, in this case the IRF will be very similar to the laser pulse. So, in this case the IRF could be 150 femtosecond or 200 femtosecond. So, and this IRF can be easily measured by the Raman scattering in this case, which if some of you are interested, then write me and I will be happy to explain. So, that is all for this fluorescence upconversion. So, we have discussed two methods basically, the TCSPC and fluorescence upconversion, and here we will finish our this lifetime measurement thing, and we will continue our discussion on other topics from the next class. Thank you very much.